Too many features can confuse AI models. Dimensionality reduction helps simplify data, improve learning, and reveal powerful business insights. Now let's look at too many features can confuse models. Machine learning models learn from features. But more features do not always mean better learning. Too many columns can make data noisy, slow, and difficult to understand. Some features may repeat the same information. Some features may add confusion instead of value. Dimensionality reduction helps simplify the data. It keeps the most useful information and removes unnecessary complexity. Now let's look at what you will learn. First, we will understand dimensionality reduction. Then we will see why too many features can create problems. Next, we will compare feature selection and feature extraction. After that, we will explain PCA, t-SNE, and UMAP simply. Then we will use business examples from customer analytics, fraud, risk, demand, healthcare, and manufacturing. Finally, we will cover when to use these methods and common beginner mistakes. Now let's look at what is dimensionality. In machine learning, dimensionality means the number of input features. If a dataset has 10 input columns, it has 10 dimensions. If it has 500 input columns, it has 500 dimensions. Examples of features include age, income, sales, clicks, complaints, and transaction amount. High-dimensional data means data with many features. This can be useful, but it can also become hard to analyze. Dimensionality reduction reduces the number of features while keeping important information. Now let's look at why too many features are a problem. Too many features can slow down model training. They can make charts and patterns harder to understand. They can increase noise in the dataset. They can make models more likely to overfit. They can also create confusion when many columns are strongly related. This problem is often called the curse of dimensionality. Dimensionality reduction helps manage this complexity. Now let's look at a simple business example. Imagine a retail company analyzing customers. Each customer may have hundreds of data points. Purchase history, web clicks, returns, discounts, location, reviews, and loyalty activity. Some columns may be very useful. Some may be repetitive. Some may be noisy. Dimensionality reduction helps summarize this large customer profile into fewer useful patterns. Now let's look at feature selection versus feature extraction. There are two common ways to reduce dimensionality. Feature selection keeps the most useful original features. For example, keep age, spend, visits, and complaints. Feature extraction creates new features from existing features. These new features summarize important patterns. PCA is a feature extraction method. The difference is simple: selection keeps columns, extraction creates new summarized columns. Now let's look at PCA Explained Simply. PCA means Principal Component Analysis. It is a popular dimensionality reduction technique. PCA looks for the main directions where data varies the most. It then creates new features called principal components. These components capture important information from many original features. Instead of using hundreds of columns, you may use a smaller number of components. PCA is useful when features are correlated or repetitive. Now let's look at PCA as a data compression idea. Think of PCA like summarizing a long report. The full report has many pages, but the summary captures the main points. PCA does something similar with data. It does not keep every original feature separately. It creates a smaller representation. The goal is to reduce complexity while keeping important variation. Now let's look at PCA Business Example. A bank may have many customer financial features: income, transactions, balances, repayments, credit utilization, and spending categories. Many of these features may be related. PCA can combine related patterns into fewer components. These components can help simplify risk analysis. Analysts can use them for visualization or model building. PCA helps reduce complexity in large numerical datasets. Now let's look at t-SNE explained for visualization. t-SNE is another dimensionality reduction technique. It is mainly used for visualization. It helps show complex high-dimensional data in 2 or 3 dimensions. It tries to place similar data points near each other. This makes groups or clusters easier to see. t-SNE is useful for exploring patterns, but it is not usually the first choice for building production features. Now let's look at t-SNE Business Example. Imagine a company has thousands of customers with many behavior features. t-SNE can help visualize similar customer groups. One group may contain frequent buyers. Another may contain discount-driven customers. Another may contain customers at churn risk. The visual can help analysts explore hidden segments. It is useful for discovery and storytelling. Now let's look at UMAP Explained Simply. UMAP is another method used for dimensionality reduction and visualization. Like t-SNE, it can show high-dimensional data in 2D or 3D. UMAP is often faster on larger datasets. It can preserve both local and broader structure better in many cases. This means it can show nearby groups while keeping some global relationships. UMAP is useful for visual exploration, clustering, and pattern discovery. It is popular in data science workflows. Now let's look at PCA versus t-SNE versus UMAP. PCA is often used for compression, noise reduction, and simpler features. t-SNE is mainly used for visualizing clusters and local patterns. UMAP is also used for visualization, often with better speed and structure preservation. PCA is easier to interpret than t-SNE or UMAP. t-SNE and UMAP are better for visual exploration. The best choice depends on your goal. Do you want simpler features, or do you want a visual map of the data? Now let's look at business example, customer analytics. Customer analytics often uses many features. Purchase frequency, average order value, discounts, returns, browsing behavior, and loyalty points. Dimensionality reduction can simplify these patterns. PCA can create fewer summarized customer behavior components. t-SNE or UMAP can show customer groups visually. This helps marketing teams understand segments. It can also support personalization and retention planning. Now let's look at business example, fraud and risk. Fraud and risk datasets can have many signals. Transaction amount, time, location, device, merchant, customer history, and behavior patterns. Some signals may be noisy. Some may overlap. Dimensionality reduction can help explore suspicious behavior groups. It can also reduce redundant features before modeling. This can support faster analysis and better risk understanding. Now let's look at business example, demand forecasting. Demand forecasting may use many external and internal variables. Sales history, price, promotions, season, weather, holidays, economic indicators, and region. Too many related variables can complicate the model. Dimensionality reduction can summarize related patterns. This can make forecasting models easier to manage. It may also reduce noise in the data. The result can be clearer forecasting inputs. Now let's look at business example, healthcare and manufacturing. Healthcare datasets may include lab values, symptoms, history, treatments, and sensor readings. Manufacturing datasets may include machine signals, temperature, vibration, pressure, and quality measurements. These datasets can have many correlated features. PCA can reduce complexity. t-SNE and UMAP can help visualize patient groups or machine behavior patterns. These methods support exploration, monitoring, and early insight. Human expert review remains important in high-risk domains. Now let's look at when should you use it. Use dimensionality reduction when your dataset has many features. Use it when features are correlated or repetitive. Use it when visualizing high-dimensional data is difficult. Use it when model training is slow because of too many columns. Use it when you want to explore hidden groups or patterns. But do not use it blindly. Always check whether it improves understanding or model performance. Now let's look at common beginner mistakes. One mistake is using dimensionality reduction before understanding the data. Another is applying PCA to unscaled numerical data. Beginners may also treat t-SNE or UMAP plots as final proof of clusters. These plots are useful, but they need careful interpretation. Another mistake is reducing too much information. If too many dimensions are removed, important signals may be lost. Always validate the impact on model performance or business insight. Now let's look at final content recap. Dimensionality reduction reduces the number of input features. It helps simplify high-dimensional data. Feature selection keeps useful original columns. Feature extraction creates new summarized features. PCA is useful for compression and reducing correlated features. t-SNE and UMAP are useful for visualizing complex data. Business examples include customers, fraud, risk, demand, healthcare, manufacturing, and finance. The goal is not just fewer columns, the goal is clearer and more useful data. To wrap up, here is the key takeaway. You now have a structured overview of dimensionality reduction in machine learning, PCA, t-SNE, UMAP explained. Review the core ideas, connect them to examples, and revisit concepts like too many features can confuse models. What you will learn: what is dimensionality? When practicing. Subscribe to Easy Machine Learning Guide if you want to learn AI through simple explanations and real industry examples.